So in this screencast, we're going to talk about intermolecular forces. But before we can talk about intermolecular forces, we need to talk about intramolecular forces. Those are sort of the forces sort of like inside of a molecule. So we can think of bond polarity. So we have different electronegativities between two different atoms. They have a net electron, they're on one side, gives rise to a bond polarity. That's sort of like a force, if you will, that's inside the molecule. Now, intermolecular force, or will be abbreviated like IF, are the forces between separate molecules. And the magnitude of these forces is usually constant. And we're going to talk about four different kinds of intermolecular forces. But first, let's sort of like talk about the consequences of them collectively. So we know from last semester that kinetic energy is directly proportional to temperature. So as I increase the temperature of something, the average kinetic energy of all the molecules in the sample goes up. So in the case of gases, we know that the total kinetic energy of all the molecules is greater than the total intermolecular force. What that basically means is you have these molecules that are flying around and they're attracted to each other by these intermolecular forces, but they're not stuck together. The reason we know they're not stuck together is because they're gases and they're flying separate, and so that means the kinetic energy is much greater than those total intermolecular force. But if we cool something down so we decrease its temperature, that eventually the molecules sort of come together and form liquids and solids. And in the liquid and in the solid state, the molecules are much closer to each other. So as we decrease the temperature, our total kinetic energy goes down, and eventually the attractive forces between the molecules is greater than the amount of energy that they have to leave the building. Boiling point is actually can be considered a rough measure of total intermolecular attractive force, because I know that to go from a liquid to a gas, I basically am breaking those intermolecular attractive forces between the molecules. And if I have to increase the temperature more, that means I have to give it more kinetic energy to get it enough to sort of like overtake those intermolecular forces. So boiling point is a rough measure of total intermolecular force. There's lots of different ones and they all kind of add up, but we can use boiling point as a rough measure. So another way of thinking about this is to imagine Carrie Ann Moss. Now, I am attracted to Carrie Ann Moss. I think she's quite beautiful. And she is just as attractive at 75 miles an hour, driving down the highway, as she is at 0 miles an hour if she's standing still. However, the chances of me, shall we say, colliding with her are much different at these two speeds. If she's moving much faster, then the chances of me sort of like striking up a conversation with her are much less than if she's moving at 0 miles an hour. So we can think of the attraction that I have with Carrie Ann Moss, but this is a constant because she's beautiful no matter how fast she's moving, is the total intermolecular force, that net attraction, and the speed that she is moving is the temperature. So as I change the speed as she slows down, the chances of me having a positive interaction with her and her staying nearby me increase. So keep that sort of in mind as we talk about intermolecular forces and temperature, because temperature, obviously, we fluctuate quite a bit, and intermolecular force is fairly constant. So we know we have three different phases of matter. So we have solids and liquids and gases. And again, solids, the individual species are held quite tightly, and so that means their intermolecular forces are very, very strong. Their attractive forces are very strong because they're not even moving. In the cases of liquid, the intermolecular attractive forces are a little bit weaker, and so the molecules can sort of like fall over each other. So, molecule A and molecule B, there's an attractive force there, but, it could also, there's some attraction between this molecule and this molecule and this molecule and this molecule, and they can kind of move around each other. Whereas in the solid phase, this molecule is attached to this one, and they are very, very stiff. They might jiggle a little bit, but those attractive forces are there. And then as we increase the temperature of this liquid, the molecules have enough energy, have enough kinetic energy to sort of like overcome that attractive force, and they sort of leave the building. So you can almost think of them as the teenagers. The liquid is the teenagers in the house, and then the gas is the 20-somethings that are finally, fly, be free. They have enough kinetic energy that they want to get out. In the case of gas molecules, they're moving so fast, kinetic energy is high enough, that they're flying so fast that the attractive forces between the two different molecules is no longer keeping them together. So we know if we're going from, in the case of going from a gas to a liquid, we know that what is happening, we're sort of like cooling it down, so we know that the kinetic energy is decreasing. And in that case, finally what happens in the liquid phase, in going to the liquid phase, is those intermolecular attractive forces are greater than the kinetic energy keeping apart. So the attractive forces, the attractive forces are, the impetus for it to come to a liquid phase exceeds that of the force trying to break them apart. So in the case of helium, helium goes from a gas to a liquid at 5 Kelvin. So there needs to be some sort of intermolecular force that is allowing those helium atoms to come together. There's going to be some glue. There's going to be some reason for those helium atoms to come together. And so far we haven't talked about any intermolecular forces except for a dipole moment. And we know that helium is just a little monatomic and spherical. It's got no dipole moment whatsoever. So what is that intermolecular force? Well, we know that a dipole is a permanent charge unevenness. So we have bond dipoles, we have different electronegativities. This atom is more electronegative than this one. We have bond dipoles. There is another form of sort of polarity, if you will, and they're called London dispersion forces. And London dispersion forces are what are sort of like a temporary charge unevenness. So, and they're usually weak, but they are everywhere. So let's sort of like talk about what one is. So here is our two helium atoms. So they have some electrons in that 1s shell and then a positive 2. And then we have another helium atom coming up nearby it, and it's also nice and symmetric. It's got its positive charge and its 2 electrons running around it. So what will happen is, at one moment in time, that those 2 electrons that are running around in this 1s orbital might be on this side of the atom. And if they're on this side of the atom for instantaneously, then there'll be sort of a partial negative and a partial positive charge. Well, this partial positive charge then nearby this helium will drag the electrons here because they'll be sort of like a positive charge. So the negative electrons here are dragged to this side of atom B, and so now we have this sort of partial positive and this partial negative, and that is an attractive force. Now the key here is that is sort of temporary, because as soon as the electrons, remember this was instantaneous for just a brief moment, so these electrons sort of like wander on back, everything gets sort of canceled out. So that's why these are usually considered very weak intermolecular forces, but not always. They can be pretty big. So for example, if we consider bromine, which has no bond dipole because the electronegativity of bromine and bromine is obviously the same. So there's no dipole moment, no permanent dipole moment. So the only intermolecular attractive force keeping the 2 bromine molecules together is this London dispersion force. And we know that the London dispersion force in bromine is pretty high because bromine is in fact a liquid at room temperature. And remember what we said, that boiling point is a rough measure of total intermolecular force, and since bromine is a liquid at room temperature, that means it has a relatively high boiling point, and since its only intermolecular force is London dispersion force, that means for bromine it's actually pretty high. Now we have a term for how easy it is for these molecules to polarize and undergo these London dispersion forces, and so we refer to it as polarizability. So something that polarizes, that has these London dispersion forces, is polarizable. Another way of thinking about it is polarizability is directly related to the magnitude of their London dispersion force. So the more polarizable it is, the greater that force. And fluorine and chlorine, so these are all our halogens. Fluorine and chlorine are gases at room temperature. Bromine is a liquid at room temperature. Iodine is a solid at room temperature. And again, in all of these cases, these molecules have no permanent dipole moment. So what else is that intermolecular? What else are those London dispersion forces a function of? Well, we know that they're always there, and they're everywhere, and they're usually weak. And London dispersion forces sort of like go up with size and elongation, basically depending on how big the particular molecule is. So in this case, we have this long chain of carbons and hydrogens on the end. This has no dipole moment because these are all linear, and this has no dipole moment. If you go back to remember how you measure dipole moments, both of these have no dipole moment. But this molecule will have greater polarizability. Because remember what polarizability is. It's sort of like a how often and how easy is it for there to be a temporary charge unevenness. Well, if you have a big long chain, that means the chances of the electrons being sort of like lopsided at any one point in time are greater the larger the chain is. If you have a very small system, like we did back here with helium, the chances of at any moment in time there being the electrons being on one side are much smaller because it's a smaller box. The larger the box is, the larger the chance of it being uneven. So as London dispersion forces, we know that we also have dipole moment. So obviously dipole moment is an intermolecular attractive force that keeps molecules next to each other. And we know that the greater the dipole moment, so we have a greater dipole moment and a greater London dispersion force. These are sort of like additive. These are our two intermolecular forces that we've talked about so far. So if this one's big and this one's big, the total intermolecular force is larger. So when we have a stronger glue between the molecules, and again, boiling point is a measure of that total intermolecular force. So one more form of intermolecular force is hydrogen bonding. So here is two water molecules, and this water molecule has an overall dipole moment, kind of going right through here, and I have my hydrogen atom, which it has a partial positive charge, and I have my oxygen from the other molecule that has a partial negative charge. And so this is sort of a dipole moment interaction, but because of the hydrogen being so small, because remember hydrogen is just sort of a bare proton,